Okay, this slide shows the plasmasphere in its two extreme states. The top one is I can't see it very well from here. The one at the top shows the quiet time plasmasphere in its puffed up state with the plasma pause at L equals 7. And the bottom one shows the storm time plasmasphere with the plasma pause at L equals 2. We have been, for some time now, concerned about the question of how the plasmasphere goes from one state to the other, and how this dynamic change in the plasmasphere may be related to what goes on in the underlying ionosphere. I think we have a pretty good understanding now of how the plasmasphere goes from this state to this state, how it recovers from the magnetic storm effects. We don't understand very well yet how the reverse process works. We have depended very heavily on our Whistler data from H station in Antarctic for this kind of study. Unfortunately, that station was closed in 1965, but since then we went back to that same area and established a new station at Saipol. And we just received the shipment of a large block of data, which I hope will help us answer the remaining questions. The recovery from this state to this state occurs by filling from the ionosphere. This depleted region here fills up from plasma flowing upward from the ionosphere on the day side. And then when the plasma rotates onto the night side, they're partially drained into the ionosphere to help maintain the nighttime ionosphere. But the draining on the night side is less than filling on the day side, so that there is a net increase in plasma content during the recovery process until the density level in the plasmasphere reaches a certain level where it just saturates and doesn't increase any further. I think the next slide illustrates this better. Let's just look at the top part first. This is deduced from Whistler's recorded at H station. I have plotted the tube content, plasma tube content here as a function of L value. And this curve shows the tube content profile after it had 1 day to recover from a magnetic storm. Then the second day, it recovers to this level, third day, fourth day, and on to the 8th day. And one thing you can notice right away is this apparent saturation level. So at any given point, the tube content keeps on increasing until it reaches this level. And at this level, the nighttime draining and the daytime filling balance each other out. So there is no further net increase. And there is a remarkably well-defined boundary separating the two regions. The inner plasmasphere, where this plasma is in a diurnal average sense in equilibrium with the ionosphere, and the outer plasmasphere, which is still filling up from the ionosphere. And notice that this demarcation line is at L equals 2.5 after 1 day of recovery, and it moves out to L equals 4 after 8 days of recovery. So it is a very slow process, and 8 days is a pretty long time in the life of the magnetosphere. There are bound to be some disturbances, substorm activities, which will tend to deplete the plasmasphere again and push this demarcation level further inward. So this demarcation between the inner and the outer plasmasphere appears to be more or less a permanent feature of the plasmasphere. The other process of how the plasmasphere gets depleted during disturbances is not well understood. We only know bits and pieces which have yet to be pieced together. I believe there are several processes involved in the depletion of the plasmasphere. One would be the peeling off of the plasmasphere by convection electric fields, which I'm sure Rick Chappell and perhaps also others will discuss later on in this at this conference. There is another important process, which is the dumping of the plasma into the underlying ionosphere. And these two processes may go on simultaneously at different local times. We don't know how this local time regime is carved up by these two different processes, but I believe the peeling off process probably works in the late afternoon local time sector, whereas the dumping into the ionosphere operates in the nighttime and morning, night and morning sector. I'll show you one example of this plasma dumping into the ionosphere. This one shows, this again comes from Whistler data. This is a tube content profile before a rather isolated substorm activity. Just started out with this. And a few hours after a substorm activity, we had a profile looking like this. And all of this is inside the plasma pause. The plasma pause is sitting farther out. L equals 5.5 or 6 perhaps. And from detailed analysis of the Whistler data, which I won't go into here, we could deduce that the process actually occurred this way. It started out with this initial profile, which was shoved inward by westward electric field. So you would have a profile looking as this dashed curve, but this was combined with a downward flow into the ionosphere, so the end result was this.